In this video, we're going to be talking about base E and natural logarithms. So just like pi and square root of 2, E is a number. E is a number, and it's approximately equal to 2.7182, so on and so forth. Okay, so E is a number, and you can find it on your calculator, just like you can find pi. And when E is in a logarithm, it is called a natural base. Natural base. When we have the natural base E in exponential equations, we're talking about continuous exponential growth and continuous exponential decay. And the inverse of a natural base exponential function is called a natural logarithm. And this can be written as f of x is equal to log base E of x, or as f of x equals to ln of x. And these two things mean exactly the same. It's just two different ways of writing it. So for example, we could have a natural logarithm that is ln of 4 equals x, and this can be rewritten as log base E of 4 equals x. And then if we wanted to write it exponentially, it would be e to the x equals 4. And these two things are saying the same thing, and this is the inverse of these. So a very common application of natural logarithms and the base E is using and looking at continuously compounded interest. So we're dealing with money, which is always a great thing, and continuously compounded interest formula is A equals PE to the RT, where A is the amount in the account after T years, P is the principal amount invested, so the original amount invested, and R is the annual interest rate. So let's go ahead and take a look at an example. It's on financial literacy. So when Angelina was born, her grandparents deposited $3,000 into a college savings account, paying 4% interest, compounded continuously. Assuming that there are no deposits or withdrawals from the account, what will the balance be after 10 years? So when we're looking at this, at any example, any word problem, we want to figure out what we know and what we're trying to find out, and identify some of the variables in there. So, since we know it is compounded continuously, we need to use this formula right here, because this is the formula for continuously compounded interest. So let's start identifying some of the pieces. So A is the amount in the account after T years, and we want to know what that is. So we don't know what A is, so we're going to solve for A. Then P is the principal amount invested. So the original amount invested is $3,000. So P equals $3,000. Then remember, E is a number, okay? Then R is the annual interest rate. So the annual interest rate is 4%. And we write 4% as, so it's R equals to 0.04 because we need it in a decimal. And now we need to tell how many years we have. So T is equal to, and we're looking at 10 years. Awesome. So now what we need to do is plug them into our formula. So we have A equal to P, which is 3,000, E to the RT, so to the 0.04 times 10. So we first need to simplify the exponent. We have 0.4. Okay, then use a calculator and remember to do order of operations, because exponents come before multiplication, and we will end up getting just about $4,475.47. So if we're looking at this, after 10 years compounded continuously, we have about $4,475 in the account. Now let's take a look at Part B. Part B says, how long will it take the balance to reach at least $10,000? So now we want to, again, identify the pieces that we know. Our P is still the same. Our P is still $3,000 because that's what we put in originally. Our A is going to be known now, right? We want our A to be at least $10,000. So A is at least all right. Now everything else stays the same. Our R is still 0.04. But this time we want to know how much time it's going to take. So our time is what is unknown. So we're going to take all these pieces and plug them in. So our A is $10,000. So we can write 10,000. And when we say at least, we're saying that should trigger that it's going to be an inequality. So $10,000 is less than our P, which is $3,000, E to the R, which is 0.04, and T. So we've set up our equation, our original equation, and now we just need to solve this. Okay, so when our unknown is up in the exponent, we have two ways of getting it down. So we can either make our bases be the same or take the log or natural log in this case because we have an E. So I think that this one, it's going to be easier for us to take the natural log, but we want to get the exponential part all by itself. So we want to get this all by itself on one side, so we need to get rid of the 3,000. So what we need to do is divide both sides by 3,000. And you're going to get 10 over 3 is less than E to the 0.04t. Okay, so now is when we take the natural log of both sides. So we have ln of 10 over 3 is less than ln E to the 0.04t. So what we have here is we have on the right hand side the natural log base E of E. So when you have the base that's the same as the number here, it can go away. So this right here can go away and we can be left with the exponent. So we'll be left with ln of 10 over 3 is less than 0.04t. Alright, so now all we need to do is solve for t. So we need to divide by 0.04, divide by 0.04, and now you can plug it into your calculator for the left-hand side, and you're going to get just about 30.099 is less than t. So what this means is that it's going to take us about 30 years to reach at least $10,000. So if you notice, this problem took a little bit more work in that we had to remember our properties of logarithms in order to solve for the unknown. Now when the unknown is just on the outside like it was over here, that's super easy. You can just plug things in your calculator, and this one just takes a little bit more work because the unknown is up in the exponent. But with practice, you'll be able to do both very easily.